Alright, so we started looking at exponential functions on the Thursday before break, and just want to real quickly look through a few of these. Remember we said that exponential functions don't have one set parent function. And the reason is because, as you can see right here, it's a to the x, and a can be a lot of different things. Okay. But do remember that the domain is all real numbers. The range, there you have an asymptote, a horizontal asymptote at the x-axis. So the range is everything greater than 0. And notice too that unless we have some kind of a shift, the y-intercept is always going to be at 0, 1. Okay? So, let's just sketch a few of these by finding some points. Okay? So, as we already said, the y-intercept on every one of these is going to be at 0, 1. But someone give me some points for, or give me a point for 2 to the x. What? 1,
4.
1, 2. What's another one?
4. 2, 4.
2, 4.
2, 4.
Okay.
3, 8.
3, 8. Okay. 3, 8. How about a negative 1? If x is negative 1, we're at 0.5. Okay. A half. All right. If we're at negative 2, we're down to 1/4. Right. Okay. So we have this horizontal asymptote. All right, and there we go. Okay, that's what that would look like.
Yay!
All right, so then we had 4 to the x, and what's the y-intercept for 4 to the x?
1, 4.
The y-intercept for 4 to the x?
0.
0, 1. Okay, and then you have the 0.14. Someone said 2. 16. Okay, 3 is going to be up at 64, so we'll stop there. If we go to the left, it's going to be negative 1, 1/4. Okay, and then negative 2 would be at 1/16. Okay, so you'll notice we're going to approach. We still have this horizontal asymptote. We're just getting there faster. Okay. All right, so there we have that. And then let's look at 0.5 to the x. Now, notice here, a is between 0 and 1. What is that going to do to our function? It's going to be a decay. Remember, these are exponential growth. When a is between 0 and 1, we have exponential decay. Now, what's the y-intercept going to be? 0, 1 still, okay? That hasn't changed. However, as x increases, 0.5 to the first is 0.5, 0.5 squared is 0.25, and so on. Notice we're approaching the x-axis on the positive side. On the left, we're going to have negative 1, 2, negative 2, 4, negative 3, 8, okay? And let's see, negative 4 will be at 16. So here is our function. Okay?
That's just a decay.
That's a decay, yeah. It's going down, it's decreasing as x increases. Okay? And then finally, 2 to the negative x. 2 to the negative x. What are some points here? What's our y-intercept?
1.
0, 1 still, okay? Now, by the way, 2 to the negative x is a transformation. of 2 to the x, right? What does it look like?
No, horizontal. No, y.
Wait, what? Just
Isn't it a
stop.
reflection over y?
Horizontal.
Very good. It's a reflection over the y-axis. So instead of 1, 2, we have negative 1, 2. And instead of 2, 4, we have negative 2, 4. And what do you know? We get actually the same thing that we got here for 0.5 to the x. Okay? If you think about this algebraically, 0.5 is 1/2, right? So that h of x is 1/2 to the x, right? And 1/2 is 2 to the negative 1 power, right? And you guys know if you raise a power to a power, what do you do with the exponents? You multiply them, so this is 2 to the negative x power, okay? And that's j of x. That's why we got the same graph. They're the same algebraically, okay? So you could actually look at a decay problem as an exponential just reflected across the y-axis, okay? All right, now, any of these, you could consider these kind of parent functions, all right? Every different value of a technically would be a different parent function, so to speak. But with those parent functions, we can transform them the same way we did our functions in the last unit. Okay? What are the different transformations? We already talked about reflections. Translations, or shifting it up and down, left and right. And what else? The dilation, stretching or shrinking it horizontally or vertically. Okay, so those patterns that you guys saw, like in the matching section on the test, the different sketches that you made of different functions, all of that still applies here. We just have a different parent function that we're dealing with. Okay? And it's important that you're able to make the connections here. Okay? So, with that being said, let's take a look at this function right here. Here we're going to deal with the parent function 2 to the x, and I've got this drawn right here. Okay? And we want this transformation of it. Okay? We have f of x equal to negative 2 times 2 to the x minus 1 power plus 1. Alright, so someone tell me one of the transformations taking place here. It's one thing that's happening.
Reflecting over the x-axis.
Okay, good. This negative right here makes it reflect across the x-axis. Very good. Okay? What's another one for you?
Move out 1 unit.
Good. The plus 1 here means that we're going to move this whole thing up 1. Alright, what's another thing?
Vertical stretch by 2.
Okay, very good. The 2, we're multiplying the whole function 2 to the power by a 2. That's going to stretch it vertically. Good. To 2 times its height, its normal height. Okay? And someone get the last one?
Moves to the right 1 unit.
Very good. Very good. The x minus 1 here means we're going to move this whole thing to the right 1. Okay? Now, a little tip here. When you're trying to sketch these, save the translations to last. Okay? Stretch it, reflect it, then shift the whole thing at the end. Okay? So what I would do if I were sketching this is the first thing I would do is to go ahead and stretch it. I'm going to stretch it vertically. That means every y coordinate is doubled. Okay? So some of the points on the original function here were, of course, 0, 1. We had the point 1, 2, and we have the point here at 2, 4. Okay? So first of all, I'm going to stretch it vertically to double its height. So, well, actually, by the way, let's get this one too. Negative 1, and what would that be? Yeah, negative 1, 1/2. Okay? So, if I'm going to stretch it to double its height, all the y coordinates are going to be doubled. All right? Doubled. So instead of 2, 4, we're at 2, 8. And instead of 1, 2, we're at 1, 4. And instead of 0, 1, we're now at 0, 2. And instead of negative 1, 1/2, we're at negative 1, 1. Okay? Now I'm not going to actually sketch the whole thing at this point. Those are just some guide points as I work to get the whole graph going here. Okay? So there's my stretching vertically, okay? Now I need to reflect it across the x-axis. Let me make this, do that red, okay? So I'm going to take the stretched points here and I'm going to reflect those. So instead of negative 1, 1, it's negative 1, negative 1. Instead of 1, 0, or 0, 0, 2, it's 0, negative 2. Here I'm down at negative 4, and here I'm down at negative 8. Okay? So I've got the stretching and the reflecting done. Okay? Now we can do the shifting. Okay? So I'll do all the shifting in purple here. Okay? So each one of these points I need to shift up 1 and to the right 1. Okay? So, and by the way, notice our asymptote, our horizontal asymptote, will also shift 1 up. So instead of being the x-axis, now our horizontal asymptote will be right here at y equals 1. All right? So now we shift up all of our points. Up 1, over 1. So instead of negative 1, I'm at 0, 0. Instead of 0, negative 2, I'm at 1, negative 1. Okay? This point goes up 1 over 1. This point goes up 1 over 1. And now that I have the final points that I was looking for, now I'm going to sketch my graph through those points. Okay? Does everyone understand what we've done? Now, I don't care if you just do points like I did. I don't care if you actually graph each one along the way. Just make sure it's very clear which one is your final answer. Okay? Cal, did you have a question?
Reflection across the y-axis, where would the negative have to be?
For a reflection across the y-axis, you would have to have the negative in front of the x. It would have to be there. Remember, that was f of negative x. So, any other questions? All right, good. So that's all I wanted to talk about as far as the graphing goes. What I want to look at today is some application, and in order to apply it, we want to think about some situations where things grow or change exponentially. Okay? we also want to think about situations where things are growing exponentially kind of periodically, like in set intervals, or what actually happens even more often when things are growing continuously. Okay, think about like the population of a city. Okay, the population of a city is constantly changing. All right, it's not like, all right, it's the first of the month, everyone move in or move out. Okay, and then we have a new population for this month. Doesn't work that way. People are just constantly moving in and out. So the change is constant. If you do some kind of investment with the bank, chances are most banks deal with things on a monthly basis. So that actually is a situation where, your money isn't going to actually grow constantly. Your money, if you invest it in a bank where you get a set amount of interest, it's actually going to do what's called compound every month. Okay? Most banks will deal with things on a monthly basis. If you have a credit card and you don't pay your balance off every month, then each month they calculate the interest based on your average monthly balance, and they charge you that interest, and then the next month you get charged interest on everything you owed before plus the interest that you just got charged. That's what's compounding. That's why it's can be dangerous to do that, because you get charged like 20 to 24% interest on a credit card. All right, so it adds up real fast. But that also, if you're investing, is a good thing. Compounding interest grows really fast. So one of the things, though, that we need in order to look at things that change continuously is this number E. Okay? Now, how many of you have worked with the number E before? Okay? A few of you. All right, so let's talk about what the value of E is, where it comes from, and then we'll look at some application. Okay? The value of E is 2.71828 and so on. Okay? And so, well, where in the world does this value come from? It actually comes from this expression right here, 1 plus 1 over x to the x power. And what happens is that value will approach this value here, 2.718, as x gets larger and larger and larger. Okay? Now, if you plugged in a 1 for x, you'd have 1 plus 1 is 2, 2 to the first is 2. Okay, obviously that's nowhere near, well, it's kind of close to 2.718, but it's not all that close. But the greater and greater values you plug in for x, the closer and closer you're going to get to 2.718. And I want to illustrate that just using our graphing calculator here. If it'll wake up. There we go. All right. So I'm going to take this function here. I'm going to plug it in for y equals x. So I have parentheses 1 plus 1 over x. And I'm going to raise that whole thing to the x power. Now, you guys can see the graph of it right here. It's another exponential function. All right, so you should have anticipated what it would look like. But let's look at what the value actually approaches as x gets bigger. And for that, we're going to use the table function. All right, so I'm going to go to second table set. I'm going to start at 0 and just start with the delta table being 1. And if I look at my table, you'll notice it's undefined at 0, which makes sense because we had a 1 over x in there. And then as we plug in, notice it goes to 2, and then 2.25, 2.37. So you can see it's increasing. Okay? But then, let's say that instead of going up by ones, we went up by 100s. Okay? Now if I look at my table, you'll notice at 100 it's 2.7048. And then 2.7115 and so on. And by the time we get to 600, it's at 2.716. You guys are seeing here what's actually known as a limit. We are finding the value, what the value approaches as x increases. I'm going to do this one more time, and I'm going to set my delta table to be 1,000. Okay, and you'll see here, by the time we get up to 5,000, we're at 2.718. And if we continue to go down here, here's 2.7182 at 11,000. Okay, and we could keep going, and obviously this doesn't show enough decimal points, but the bigger and bigger we made x, the more of these decimals would match up with this value here. Okay? Now, our calculator actually can give us e, if we quit out of this, above the ln button. This is our natural log, which we'll talk about later. But right above the ln is a little e to the x. And if you want the value of e, you can just hit that and put e to the first power, and there you have it, 2.718. Okay? If you are using your calculator to find a value that involves e, use the e to the x button. Do not just type in 2.718. Okay? Use the e to the x button. Be precise. Let me help you out here. If you are not using a calculator, you can leave your answer in terms of e. Okay? Just like you can see here on these points, they didn't figure out what 1 over e squared equaled, they just made it 1 over e squared and left it. It's kind of like leaving things in terms of pi when you were dealing with circles. Okay? So, that's what e is. So let's look at how e is used. I mentioned how things can grow or change exponentially, either at set intervals or it can change continuously. And that's where interest comes into play. Okay? If something is growing or decaying constantly, we'll use a natural exponential function to model it. So I'm using the example of interest here. We already talked about interest briefly in terms of a credit card or in terms of your bank account. Okay? Continuously compounding interest uses e. Alright? The formula here, and this is a formula that you should know, is the amount at a given time t equals p times e to the rt power. Okay? That's compounding continuously. Okay. Now, like I said, for interest, for money, most banks don't use this. But this same formula, the concept behind this same formula can be applied to any situation where things are changing continuously. Okay? Now, when things are changing periodically or at a set interval of time, we would use this formula. And by the way, remember what e was. E was that 1 plus 1 over x to the x. Okay? Well, look at here. Here you see a 1 plus something over n to a tn power. See how e is kind of in there? And n is the number of times we're compounding. Well, if that number of times we're compounding approaches infinity, that's where we're getting the e from. Okay? So I want you to see how these are related. They're not just two random formulas. They're totally unrelated. There actually is a connection here. Okay? But let's talk about what the different values in the formulas stand for. Okay? P is your principal. Okay? Principal is a financial term, and it stands for the starting amount of money that you have. Okay? The starting amount. If you're investing, it's whatever money you put into that investment. If you take out a mortgage on your house, or if you're borrowing money some other way, the starting amount that you borrowed is your principal. Okay? This is also, sometimes you'll see it written as A sub 0, the amount at time 0. Okay? The amount when t equals 0. Okay? Now, your interest rate is R. That's a percent, okay? And it's always going to be an annual rate, okay? When you're using these formulas, R needs to be an annual rate. That means it's a rate for a whole year, okay? So I mentioned earlier, a credit card might charge you 24%. They're not going to charge you the full 24% every month. That's how much it would charge you over a whole year. So if it's 12 months in a year, 24% for the whole year, you're actually getting charged 2% every month. Okay? But you want the annual interest rate. The time also has to be in terms of years. Okay? We need to be consistent with our units of measure here for the time. Interest is in terms of a year, time is in terms of a year. Then you have N. N is how many times you're compounding every year. Okay? And there's some terminology some of you might not be familiar with. Okay? Common values of N might be 1, 2, 4, or 12. Okay? So, if we're only compounding once every year, that means we're compounding annually. Okay? Just like an annual rate of interest is for the whole year, annually means we're going to be compounding every year. Okay? That's pretty simple. If we're compounding twice a year, 2 times a year, that means we're going to compound every half year, right? What's the prefix that means half? Semi. Okay, like a semicircle is half a circle. So we would do it semi-annually. Semi-annually. Okay? When n is 4, if we cut something into 4 pieces, there are 4 quarters, all right? So if we are compounding quarterly, n would be 4. And then, of course, if we're using 12, we must be compounding monthly, okay? Monthly. All right? What?
I said the right thing for once.
Good. All right, so those are our different values of n. Those are terms that you should be, familiar with. Okay. So let's real quickly actually use these here to do part of this problem here. We're just going to do part A. All right. Says there are 3 options for investing $500. Now let's stop right there. Okay? Let's stop right there. And if we're investing $500, what would we call that $500? That's our principal, okay? So that's our principal. So, and you'll notice that both of the formulas start with P. So I'm actually going to write down that 500 for all 3 formulas. It's going to be 500 times something there, 500 times something there, and 500 times something there. Okay? But we have three options. The first of these is 7% compounded annually. All right, so let's stop and write a function for that. Which of the formulas are we going to use? The second one, because we're compounding annually, and n would be 1. All right, so we have 500 times 1 plus 0.07 over 1 to the t times 1 power. Now, notice here for part A, they want us to look at a 20-year period. Okay, so we're going to put in 20 for t, and of course it'll be times 1 because n was just 1. All right? So what would that equal? $1934.84? Okay, and we're dealing with money, right? So the smallest unit is the penny, so you should round to the penny, unless you're told to do it otherwise. Okay? So just round to the penny. Okay? All right, how about our second option? It's 7% compounded quarterly. So what's going to be the difference between the first one and the second one?
T will be 4. No.
What's
wrong? N would be 4.
Good. Okay, good. The n would be 4. So it's going to be 1 plus 0.07. And this is where those of you using your calculators, if you use the copy paste, you just have to change one little or two little parts to it. So it'd be 0.07 over 4 and then 20 times 4. Okay. And this ends up being 2,000
2003.
19 cents. Okay. All right, so we made a little bit more by compounding it more often. Okay. We made a little bit more by compounding it more often. And then we have the last one, 7% compounded continuously. All right, so how's this one going to differ from the previous two?
Use the first equation.
Good, we got to use the first equation there. So it's 500 times e to the 0.07 times 20 power.
27.59.6.
Okay? Yeah, we'll make sure we round. So $2,027.60. Okay? So just for letting it sit there for 20 years and not touching it, you have 4 times as much money. Okay?
How come we use the first equation?
Because the first one we wanted continuously, and this one has the e. That's how we get the continuous. All right. So you guys can kind of see a general trend here. If we have the same principal, the same time period, the same interest rate, then the more you compound every year, the more money you're going to end up with. Okay? And that difference is going to be greater and greater the longer you let it sit there. Okay? So, if you had done this just for like 6 months, the difference would have only been maybe a couple bucks. Now the difference is up to, here we had like $67 difference and $24 difference. Okay? So and then the longer period of time you're talking about, the greater that difference will be. Okay? So, compounding interest is a really kind of powerful thing. Okay? another application is the idea of half-life. Okay? And believe it or not, this half-life idea is the same as our, it's based off of the same formula that we just worked with. However, we can kind of learn a different one to simplify matters a little bit. The amount at any given time when we're talking about radioactive decay is going to be your starting amount. Here's the A sub 0 I was telling you about, A sub naught, times 1/2. We know this is a decay because A is between 0 and 1. Alright? And it's 1/2 to the T divided by K power. Alright, now you may see letters other than K used, but whatever this value is here, that K is the half-life. Now the nice thing about this is as long as you're consistent in talking about your time periods, the half-life doesn't have to be in a specific unit of time. Half-lives could be in years like they are here, they could be in months, they could be in days, they could even be with really unstable radioactive isotopes, they could be matters of seconds. Okay? In fact, like a lot of those ones at the real bottom of the periodic table, you know, like, I forget what numbers they are, like 190 or 198 or whatever they are. Okay, those are ones that chemists have been able to basically force into existence, and they exist for a matter of seconds, and then they decay until they're actually something else again. They basically bombard atoms with protons until one sticks. That's really oversimplification. I don't understand the whole process, but that's kind of what they do. So a half-life could be a matter of seconds. But looking at this, and here we're given a function Q for a mass in grams of radium, and the half-life is 1,599 years. Okay, so you'll notice here we have T divided by 1,599. Alright, so how much did we start out with? 25 grams, okay? 25 grams. Notice A sub naught is the part in front of the 1/2, so there's the 25 right there. Okay? Now for part B, I want you to think. Okay? Let's actually think about a little graph of this. We're not going to do part C with a graphing calculator, we're just going to kind of approximate it here. We just said at time 0 we have 25. Okay? We want to find at 1,000 how much is left. Okay? Let me ask you something though. Half of 25 would be at 12.5. When is that going to happen?
After the first year, 799 years.
Yeah, wait, what?
799 years.
No,
After the first year.
not after the first year.
It'd be after the half-life.
After the half-life. So when the time is 1,599, I'm at 12.5. That's what a half-life is. Okay, does that make sense? Now let's say I went out here to 3,198 years. 2 half-lives. How much will I have left? 6.25. It's not going to be 0. It's not half of what the original was down again. It's half of what I was at. So each time it's cut in half. Alright, so there's that point right there. So, what do I know about how much I should have at 1,000?
Between 25 and 12.
Yes, good. It should be between 12.5 and 25. And the reason why I'm pointing this out here, guys, is it's really easy to punch this into your calculator wrong. When you do the t divided by 1599, it's easy to accidentally put just the t in the exponent and then divide the whole thing by 1599. Alright? So be careful and think when you get that answer from your calculator, does this make sense? Alright? So what do you actually get when you punch in 1,000?
16.2.
16.2 what?
0621.
0621?
206.
Oh, 206. Okay, so we'll just do a 16.21, 2 decimal places. And that puts us about right there. And you can see the exponential decay to our model here. Alright? So that's what we've got. Does that make sense?
So would you plug in the 1,000 to T or K? T, right?
T, yeah, because we already know K is 1599. That's not going to change at all for this problem. But the T will change. Yeah. Okay. Any other questions? All right. Good. Good. All right. So a lot of this is taking similar ideas, like this formula here, P e to the RT. We could apply this not just to money, but to populations of a city or population of a bacteria in a petri dish. Okay, we could apply this to half-life even, with a negative rate of change. Okay, or not even just half-life, but any decay problem. Let's say this town is kind of going downhill and people are moving away and we're losing 3% of our population every year. Our rate would be a minus 0.03. And that's going to give us a decay problem then. Alright? So we could then use that to approximate different things. So I have you memorize these two formulas, not only because they're commonly used in finance, but also because this one in particular is used a whole lot in a lot of different contexts. Okay? Alright. That's going to be it for today. Alright? Take a look at the class website or the Sunday Post for your practice.